Okay, so welcome to this 12th lecture in this course on algebraic topology. We're at the University of New South Wales, and I'm Norman Wildberger. Today I'm going to do two sort of different things. I want to talk about duality for polygons in the framework of these turning angles that I introduced in the last lecture. And then I want to go to the first of our applications of winding numbers and talk about a very famous theorem, the Fundamental Theorem of Algebra. So I want to recall what I did last time. It was a little bit unusual, so it's worth reminding you. We defined a new kind of angle where we said that the angle all the way around was going to be equal to 1. Okay. And we call this, instead of an ordinary angle, we call this a turn angle. And we also allow, in the other direction would be -1, and we allow equal subdivision, so we can talk about fractional turn angles. So for example, have a look at pentagon. That's supposed to be a regular pentagon with one turn angle tau 1 there, tau 2, all in the positive direction, tau 3, tau 4, tau 5. And say over here also, we can also talk about the external turn angle, or the curvature at this vertex. So I called it mu1, let's say, where these lines here are obtained by going perpendicularly from the sides there. Okay, so I remind you that in this kind of situation, the tau 1 plus mu1 added up to 1/2. And therefore, the 5 turns, tau 1 up to tau 5, added up to 5/2 minus 1, which is 3/2. And from that, we can deduce that each of the ti, or the tau I, has got to be 3/2 divided by 5, or 3/10. So that's the internal turn angle in a regular pentagon. And conversely, or in addition, the total curvature, we'll just check. The total curvature is 5 times, what is the external fellow? Mu1 will be, well, if they add up to 1/2, then mu1 would better be 2/10 or 1/5. And so the total curvature is 5 times 1/5, which is 1, which is what we expect for any convex polytope. So we are now in a position to analyze ordinary familiar triangles in sort of a new way. So for example, if we take a 90-60-30 triangle, a very familiar triangle to all students, if we think about how would we describe that in terms of turn angles, well, 90 degrees is, as we saw last time, that's going to be a turn angle or tangle of 1/4. 60 degrees is 1/6 of the way around the circle, so it's 1/6. And 30 degrees would be 1/12 of the way all the way around. And the sum of the turn angles, 1/4 plus 1/6 plus 1/12, that should equal 1/2, and I think it does. And for those of you who teach young children, let me remind you that when children learn about fractions, one of the simplest ways that they can visualize what a fraction is by dividing a pi up into equal pieces. So if you want to teach a child what is 1/6, there's perhaps no better way than divide a pi up into 6 equal pieces. And each one of those pieces is 1/6 of the total. And it's very natural then for the angle at one of these things to actually be the same as the fractional piece itself. So we're making the notion of angle coincide or correspond with their intuitive idea of fractions. So in fact, turn angles provide a good place for young people to practice their arithmetic with fractions. It's a very natural place where they can practice. Instead of adding 60 and 30 to get 90, they can add 1/6 and 1/12 to get 1/4. Just make that remark. There's another thing I would like to introduce, since I'm sort of establishing notation here, and that's a little bit to do with an ambiguity which is in the current treatment of angles. In the current treatment of angles, one has actually two separate kind of angles that are used. There's an angle where the angle is always in between the range 0 to 2 pi. And then there's another kind of angle like I'm talking about where the values are allowed to get bigger than 2 pi or maybe less than 0. These are these two sides of things which really ought to be separated, in my view. They're really two natural, different usages of angles. So this one here I like to think of as being a dynamic turn angle because it actually represents the motion of something that's going around. There's also a corresponding static notion, which I'll mention, okay, which is what you do when you're measuring simply two sides with no reference to a motion from one to the other. So for example, suppose that we just had that as the initial and let's say okay, that as the final, and let's call that ray number 1 and ray number 2. We wanted to talk about the turn between the ray 1 and the ray 2. What would it be? Well, we're not saying how we get from here to here. We're not saying that we go this way. We could also be going this way or this way. So in this case, it makes sense to just have a number that only depends on the two boundaries. And one way of doing that is to say that the static turn is defined by being in the range between 0 and 1. Agreeing that the static turn is going to be the dynamic turn mod 1. Okay? So I don't have a particular notation, but maybe we could put static here. Okay? So the static turn would be, by definition, the ordinary turn mod 1. We could call that the static turn angle. And how might we represent that? Well, to distinguish it from the turn angle, instead of drawing a solid arc, we could maybe draw a dotted arc and still put a little arrow. That's just one possible suggestion. Okay? So this might be a static turn angle of tau equals maybe a fifth. Yes?
Any angle going around the other way as well?
Well, we could be. So the question is, how do we know we're not going around the other way? So when we write this, we would say that this is equal to this one here, or it's equal to going around 2 1/5 times.
Not to negative 1.
Not to?
Negative 1.
No, not to negative 1/5, because it's still oriented. We're still going from R1 to R2. That's the first, that's the starting, that's the ending. So I'm thinking of like this tau s is really tau s of R1 and R2 in that order.
But it could be like minus 4/5.
It could be minus 4/5. In fact, it would be equal to minus 4/5. So 1/5 is equal to minus 4/5 mod 1. So each of those is a valid representation for this. So we can also say this is minus 4/5 if we wanted to. Okay, so here are a couple of problems to try out with these turn angles. In the first problem, we divide a circle into n equal pieces. We mark out 3 points, A, B, and C, separated by k of the pieces, m of the pieces, and n of the l of the pieces, where k and l and m add up to n. And we ask what are the turn angles of this triangle that we're forming in terms of k, l, and m. In problem 15, we also have a regular subdivision of the circle, in this case into 9 pieces. And we are going from one piece over 2, and then over 2, and then over 2. So that's that's a non-convex polygon with 9 sides, which we might call Pn9 sub 2. And that non-convex polygon has a turn angle there of some tau. And I ask, what is that turn angle? And what is the curvature at each vertex? So if you made something like this, what would be that curvature? And what is the total curvature of the entire polygon? And you could ask the same thing for, say, P9,4, and somewhat more generally, can you find a formula that works not just for 9 and 4 and 9 and 2, but for n and k, where n and k are relatively prime. Okay, I want to talk a little bit about duality of polygons and cones. This is a useful thing for undergraduates to know, I think. That's often not treated in standard courses. So let's start with a cone. So in the plane, a cone is what you get by having 2 vectors v1 and v2, let's say, and considering the rays generated by those vectors, and then the convex hull of those 2 rays. All right, so that's a cone, a convex cone. Now, the vectors v1 and v2 form a basis for the 2-dimensional vector space, which is really the same as our affine space, except that there's an origin added. Okay, that's the difference between an affine space and a vector space. Topologically, they're the same, but with the vector space, we have an origin associated to it. So we can talk about vectors and bases. And now there's an interesting notion of a dual cone. So first of all, the dual basis is another pair of vectors, W1 and W2. It's another pair of vectors which have these properties. That W1 is perpendicular to V2, and V1 dot W1 equals 1. The dot product between V1 and W1 is 1. And similarly, W2 is perpendicular to V1, and its dot product V2 is 1. So what does that mean in this case? So W1 is going to be perpendicular to V2. It's going to be in this direction. Its dot product with V1 has got to be equal to 1. So it's in this direction. And it's so that the dot product between here and here is equal to 1. So maybe W1 might look like this. Okay? That being perpendicular. And what about W2? Well, that's going to be perpendicular to V1. So it's going to be in this direction. But it's got to be in this direction because its dot product with V2 has got to be 1. Now, since V2 is a bit longer than V1, W2 to compensate has got to be a little bit shorter. So W2 might look like this. Okay. That's the notion of going from a basis to a dual basis. And of course, now that we have that dual basis, we can talk about its convex hull, or the cone generated by it, which in yellow will be all of this. So that will be the dual cone. Okay, so now let's suppose that we have a polygon. And I'm going to draw it in a particular way. So first of all, there's going to be the origin. And I'm going to draw a unit circle. That's a unit circle, or S1, in the plane. And my polygon is going to, in this case, look like something like this. There, maybe down to there, maybe down to there, over here, there. Okay, so A, B, C, D. Okay, it happens to be a four-sided polygon, but this works for it in general. Polygon A, B, C, D. So the first thing I note is that there are some cones associated to any polygon. This is a four-sided polygon. There are 4 vertex cones. Namely, at any vertex, we can look at the cone generated by the 2 edges at that vertex. Okay? So for example, at the point A, that cone that extends in that direction, that's the vertex cone at A. There's also another kind of cone that's associated to the polytope, or the polygon, for what we might call face cones. What's a face cone? It's what you get when you look at a face from the origin. So there's the origin. It depends on the notion of origin. We can look at, say, the face AB from the origin, and that's also going to be a cone. So that's a face cone for the edge AB. And now I'm going to do something interesting, which is called duality. A polygon like this has a dual polygon. And this is important in a number of different areas of mathematics, and linear programming, and in geometry. And so I want to tell you about it. So the notion of the dual polygon. Well, we've already talked about duality in the context of the Platonic solids. You may remember that I said that the dual of a Platonic solid was another Platonic solid obtained by looking at the centers of the faces. We're going to do something similar here, but a little bit more canonical. So what we do is, let's say we take an edge, like AB, and for each edge, say AB, we construct perpendicular vector. Let's call it OX prime. So there's a perpendicular vector with X prime on the edge. With X prime on AB. And now I'm going to I'm not going to use that X prime. I'm going to use a different point. I'm going to invert that point in the circle. You remember when we talked about inversion, I talked about this process of inverting in a circle. So there's some other point, in this case X, we'll call it X out here, which is the inverse of X prime with respect to the unit circle. So now we let X be I of X prime, where I is inversion in the unit circle. All right, and we can do that for each of the edges. And what does it mean in terms of, say, linear algebra? The inversion can be written as OX prime, that vector, dotted with the vector OX, equals 1. It's another way of saying that. It's in the same direction, but the dot product, or the product of the two lengths, is equal to 1. Well, that means, however, that since this is perpendicular, that if we take the vector OB, that it's also has dot product 1 with OX. And OA dot OX also equals 1. Because the difference between this one is this one, and that one's perpendicular to OX. Okay, so what happens? So let me try to show you where these other points are. So there's perpendicular, and then we have to go out. Maybe we get a point like Y over here. And then over this one, we go over here, and then we go out. Some point, say Z. And this point perpendicularly, and then that inversion will be there, so maybe ZW. So we get a new polygon, X, Y, Z, W, and back to X. So if we do the same for the other sides, then we get the dual polygon X, Y, Z, W. And this is a very interesting relationship between the polygon, the ABCD, and the new polygon X, Y, Z, W. This duality depends, however, on our point O and our choice of unit circle. So it depends on O and our normalization of our unit circle. So I'm going to leave the following facts for you as an exercise. Not a problem, but just something to think about. The first fact is that this duality is an involution, is involutory. It means the dual of the dual is the original. So let me just illustrate that. For example, suppose that I was going to take the dual of the blue one. Let's say I want to take the dual of this side here. Okay? So I'd have to draw a perpendicular. Well, this thing here is perpendicular. So I had to invert this point in the circle, and then I would get that point A. The second fact is that the vertex cones and the face cones of our original polygon, let's call it P, have the same shape as the face cones and vertex cones of, let's call this dual P prime, the grade 1 P prime, blue one. So in particular, if we look at, say, the vertex A, and we're interested in that turn angle tau there, then well, I think you can see that this line here that we used to construct W from, this was perpendicular there. So if we extend it, we go perpendicularly. And this one here was perpendicular to this one. So these two make a vertex, which is the same kind of vertex that we use to define the curvature up here. So this, might call it mu. That's going to be mu there too. Same shape. Maybe I should say opposite shape. All right, I'll let you think about that situation. It's well worth playing around and just drawing a few examples and seeing how that goes, that duality. So I strongly suggest that you actually get a ruler and compass and try to draw a dual of some polytopes. See what they look like.
Do we have to assume that one of the original vertices of the polygon is not O?
Yes, if it's O, then you ending off at infinity. So O wants to be off the actual edges or vertices. All right, so now I want to talk about some applications of winding numbers. And the first and most important application is to the Fundamental Theorem of Algebra. Which is probably the most important application of algebraic topology. And of course, it's a very famous theorem that goes back to Gauss. Euler thought about aspects of it. It's a theorem that pops up every few years. Someone comes up with a new proof of it. So what is the fundamental theorem of algebra? Well, it says that if you have a polynomial, let's say f of z, and I'll use this polynomial as an example, z to the 6th minus 3z to the 5th plus 7z squared plus 11. And if you plot that particular polynomial over the usual rational numbers, it looks something like, in this case, something like this. That's roughly about 2 there, minus 2, about 50. So this is a polynomial function. It does not have any zeros. You cannot find a real number or a rational number that you plug in here that you get anywhere near 0. But the fundamental theorem says that if we go to the complex numbers, we can find a 0. Okay. So the complex numbers for us are going to be the rational complex numbers. So this is what I mean, things of the form a plus bi, where a and b are rational numbers. Now it's usually stated, the fundamental theorem is usually stated in terms of real numbers and complex numbers in the sense of real complex numbers. So the usual formulation involves the more familiar complex numbers, things of the form a plus bi, where a and b are so-called real numbers. Well, real numbers are not at all so real, despite the name, which is a little bit of propaganda. In fact, it's a lot of propaganda. There's actually serious logical problems with the real numbers. And these logical problems are swept under the carpet in most courses, and most undergraduates don't really learn what the problems are. But you can maybe suspect that there is a problem because you probably don't know any place where you could open up a book and find proper definitions of what exactly real numbers are, of exactly how you perform operations on real numbers, and proofs that the operations obey the laws that we want them to obey. And if you actually start looking in detail in those things, you find a lot of very serious problems, which is the reason why you don't find chapters in books that deal with these things. Now, this would take me a lot to explain, and in my Math Foundations series, I will eventually explain all that and lay out very clearly, I hope, the difficulties with real numbers. But for now, just play along with my idiosyncrasies. And I'm going to try to frame this in terms of rational numbers. So I'm going to give you a purely rational formulation, convincing you perhaps that the fundamental theorem of algebra really doesn't have anything intrinsically to do with real numbers. So here is a statement, theorem. Suppose that f of z is a rational polynomial. That means its coefficients are rational numbers of degree at least 1. Let's let n be a natural number. Then there is a number a plus bi belonging to our complex rational numbers such that the quadrants of f of a plus bi is less than or equal to 1 over n. Where, I remind you, the quadrants of a complex number a plus bi is a squared plus b squared. It's more natural to work with this than the length of the vector because this is an algebraic quantity. So what is it saying? It's saying that if we think of the function as a mapping from complex numbers to complex numbers, it's our polynomial, then you give me an n, let's say 1 million. That means I'm going to have to draw a little circle around there, which is the quadrants. Those complex numbers have quadrants less than or equal to 1 million. Okay. And what I'm saying is that I can find a rational complex number out here somewhere in here, so which is mapped close to 0 in the sense of within 1 over n in quadrants of 0. So that's the fundamental theorem of algebra, as far as I'm concerned. Okay, so now let's prove it. Well, I'm going to prove it by pictures. This is maybe not the most rigorous proof one could imagine, but I think there's nothing in it that's substantially problematic. So it's a proof by pictures. And using the notion of winding number. Of a curve. Okay. So we'll think of our polynomial, just like over there, as mapping from C to C. And we're going to get our friend to draw our little circle there of quadrants less than or equal to 1 over n. So this is quadrants of z less than or equal to 1 over n. We want to find some complex number over here, which under the transformation f is sent into this circle, into this disk. Okay, so what we do is we start by looking at circles. We're going to look at circles over here. That's what we're going to do. It's all happening about circles. So first of all, we look at 0. And we look to see where does 0 go. Well, in the example that I asked, 0 was 11. Okay, so maybe f of 0, maybe it's 11 in my particular example, but it can be anything it wants to. Of course, if that's 0, then we're done. So we'll assume that that's off somewhere. And now what we're going to do is we're going to look at what happens to the images of these small circles. Let's call a circle like this C sub epsilon. Okay? Circle of radius epsilon, or maybe quadrants epsilon. What's the image of a little circle like this going to be? Well, we don't really know, but except that we know that it's going to be close to 11 if epsilon is small. So for very small circles, this is a continuous function. So the image is going to be some little curve over here near 11, at least for small epsilon. So here's f of C epsilon. And now I'm going to look at the next larger. I'm going to increase my circle. So I'm going to look at C epsilon prime, a slightly bigger circle. Okay. That's going to be some slightly different curve. You can even wind around, I don't really care. So there's f of C epsilon prime. And we're going to watch the images of these things as these circles grow. And we've parked our friend right here to tell us if these images ever go inside the disk. As soon as one of these images goes inside the disk, he'll yell to us, ring a buzzer, and we can stop. We've essentially found our approximate 0. Okay, so now we're going to let this process grow, and we're going to let epsilon become bigger. And then now we're going to let time evolve, and we're going to look at what happens when the epsilon is replaced by a very big number. Okay, so now, much later, we are talking about a circle C, whose, let's say, quadrants is some big R. And by big, I mean R might be 1,000,000. If you like, you can think of radius. Let's talk about radius 1,000,000. Okay, we're used to talking about radius. So this is a circle of radius roughly 1,000,000. Okay, what do we know about its image under this map? Well, the particular polynomial that I was looking at was something like z to the 6 minus 3 z to the 5th plus 11 z squared. Oh, no, not 11. 7. Okay, 7 z squared plus 11. It doesn't matter what this is, but this degree we know is at least 1. Because we're assuming it's a non-constant polynomial. It's a degree at least 1. So the question is, what happens to this circle under this polynomial? Well, we're going to answer a simpler question. We're going to look at another map, the map g of z equals just z to the 6. That's a much simpler map to understand. What does it do to this big circle? Well, the image of a circle under the power z to the 6 map is very easy to understand. It's another circle whose radius is even bigger. Okay. This circle has radius, well, but if that circle is radius r, then this circle will have radius r to the degree, in this case 6. But moreover, as we go around this circle once, the image under the z to the 6 map goes around 6 times as fast. So it winds around 6 times. The image winds around, in this case, 6 times. 6 is the degree of the polynomial. Now what about these other terms, though? We're really interested in f of z, not z to the 6. Okay, so let's have a look at, say, this next term, z to the 5th times 3. Okay, if z is on this big circle of radius 1 million, this big circle here has radius r to the 6th. Where is r to the 5th in comparison to this?
Inside.
It's inside, but r is 1 million, right? So if this is 1 million to the 6th, where is 1 million to the 5th? Well, it's 1/millionth the size of 1 million to the 6th. Right? 1 r to the 5th is 1 over r times r to the 6th. So this r to the 5th term is 1/millionth this radius. In other words, it's invisible, or almost invisible to us. And even if we multiply by 3, it's still essentially invisible to us. What about the term z squared? Well, that's even much, much, much smaller. That's off our page completely. So, the image of this and the image of this map differ only by some small wiggling. The image of f of z will be just the same as the image of g of z, except that there might be some slight wiggling due to these small terms that move it around a little bit. So there's the image of f of z going around 6 times. So the image of f of z is almost the same as the image of g of z. So therefore, it winds around 6 times. So that's now the basic of the argument. So we started off with very small circles. The small circles had images around here. These curves have winding number 0 around the origin. Remember, the winding number is the number of times the curve goes around the origin. So these curves have winding number. The winding number of these curves around the origin is 0. And now we're increasing this gradually, gradually, gradually. The curves are doing something. And finally, when we get to this very big value, our big image has winding number of gamma, let's say gamma prime, equal 6. It's gone around 6 times. Okay, so how can you go from something that winds around 0 times to something that winds around 6 times? The only way you can do it is if the image crosses the center. The image has to cross the center, and our friend who's watching this neighborhood is going to see the curve pass through his little neighborhood that he's watching. Because if it didn't cross through here, then the winding number would always be the same. The only way the winding number can jump from one value to another is if you actually cross the place where you're winding. In fact, not only does it cross once, we see that in general it's going to have to cross 6 times. Okay. So for the winding number to jump, from 0 to 6 in this case, the image must cross our neighborhood of 0, our epsilon neighborhood of 0. All right, so that's sort of a pictorial argument of why the fundamental theorem of algebra is true. It's an important argument. It's a topological argument. It uses the topology of the plane, and it uses the idea of the winding number of a curve. And it's a number, I think, it's a proof that undergraduates should see, because the fundamental theorem is used in many different applications in undergraduate mathematics. It's good to have a proof of it, that you can at least have some idea that it's going to work. All right, so next time we're going to look at other applications of the winding number to other more exotic theorems. So I'll see you then.